We have now seen various ways of defining regular languages, so it's time to summarize some of their main properties. First, let's recall the various different ways of defining regular languages that we have seen. Saying that the language is regular is equivalent to saying that it can be defined by a deterministic finite automaton, which again is equivalent to saying it can be defined by a non-deterministic finite automaton, by a right linear grammar, a left linear grammar, or a regular expression. All these statements are equivalent. They all give rise to the regular languages. Having various ways of defining regular languages can really be helpful if we want to prove properties of regular languages. We've already seen some of that. If you recall, we have proven that the complement of a regular language is regular again. And this is very easy using deterministic finite automata. We can simply switch the final and non-final states. This is much more complicated using non-deterministic finite automata. On the other hand, we've also proven that the reverse of a regular language is regular again. And we've proven this using non-deterministic finite automata by turning around all of the arrows. And here non-deterministic finite automata are really helpful because turning around the arrows in a deterministic automaton doesn't give us a deterministic automaton again. So depending on the property that we want to prove, a different definitional mechanism may be better than another. So certain properties are very easy to establish with regular expressions, for example. So let's have a look at some of the elementary properties of regular languages. The class of regular languages is closed under various operations, and some of the basic operations are shown on this slide. It is closed under union, intersection, concatenation, difference, complement, cleaning star, and reversal. So if L1 and L2 are regular languages, then also their union is regular again, the intersection, the concatenation, and the difference of L1 and L2 are regular again. If L is a regular language, then the complement of L, the cleaning star of L, and the reversal of L are all regular languages again. For many of these properties, we've already seen proofs using finite automata. So we've used finite deterministic automata to establish that the union of regular languages is regular again, likewise for the intersection and the difference. We've also used finite deterministic automata to show that the complement of a regular language is regular again. We've used non-deterministic finite automata to show that the reversal of a regular language is regular again. For many of these properties, there are very simple proofs using regular expressions. So let's have a look at that. Since L1, L2, and L are regular, and we know that the class of regular languages is precisely the class of languages definable by regular expressions, we know that there exist regular expressions R1, R2, and R, such that the language defined by R1 is L1, the language defined by R2 is L2, and the language defined by R is L. So we have regular expressions for these languages. Now, if we want to establish that the union of L1 and L2 is regular again, it suffices to find a regular expression that expresses this union. And this is of course very simple. We can simply take the regular expression R1 plus R2. We know that the language associated to R1 plus R2 is precisely the union of the languages of R1 and R2, which is L1 and L2 by assumption. So this is a very simple proof that the union of two regular languages is regular again, and it just uses the fact that we know that regular expressions give rise to precisely the regular languages. Similarly, we can find a regular expression for the concatenation of L1 and L2. This is precisely the language of R1 times R2. So we know that this language is regular, and this is precisely the concatenation of L1 and L2. We can do the same for the Kleene star. We can simply take R star. For the complement, this is more difficult using regular expressions. So for the complement, the easiest proof uses deterministic finite automata. And we've already seen how to do this. We simply take a deterministic finite automaton for the language L, and we flip the final and non-final states, giving rise to a deterministic finite automaton for the complement of the language. The intersection of L1 and L2 is also difficult to express using regular expressions. However, we can use that the intersection can be expressed using the operations above. And in particular, the intersection can be expressed using the complement and the union. The intersection of L1 and L2 is the union of the complements of L1 and L2, and then we take the complement of the result. So since the intersection can be expressed using union and complement, and we know that union preserves regularity and complement preserves regularity, therefore the expression on the right must be a regular language again, so we can conclude that the expression on the left, the intersection, is also a regular language. And we can do the same trick for the difference. The difference of L1 and L2 can be expressed using intersection and complement. It is the intersection of L1 with the complement of L2. And again, we know now that the intersection preserves regularity and the complement does. So the expression on the right is a regular language. Therefore, we have established that the difference of the languages is a regular language. And finally, for the reversal, you can establish that the reversal of a regular language is regular again using regular expressions. It is possible to define inductively the reversal of a regular expression, but the easiest and most intuitive proof, at least to my taste, uses non-deterministic finite automata. If you recall, we have proven that we turn around all the arrows in the automaton, then a forward path becomes a backward path, and we swap final and starting states, and thereby we obtain a non-deterministic finite automaton for the reverse of the language. So for many of these properties, regular expressions are very convenient to establish the properties of the regular languages. For some of the properties, deterministic automata are easier, and for some of the properties, non-deterministic automata are easier. So depending on the property that we are proving, we use the formalism of regular languages that makes it most easy for us. Next, we're going to look at decidable properties of regular languages. Roughly speaking, a property is decidable if there exists an algorithm or a program that can tell whether the property holds or not. We will make this more precise when we are talking about Turing machines at a later point. But for the moment, it's enough if you understand that decidability means that you can write a program that answers yes or no. Now, we are going to talk about decidable properties of regular languages. And strictly speaking, we have to be precise in what form these regular languages are presented to the program or algorithm. For instance, if we want to ask whether a regular language is empty, and we want the program to tell us yes or no whether the language is empty, then we have to say how do we give the regular language to the program. A regular language can be infinite, so we cannot give the entire infinite language to the program. We have to give a finite description to our program. And what we mean if we say that a property of a regular language is decidable, then we mean implicitly that the regular language is given as a finite automaton to our program. Actually, it's not so important that this is a finite automaton. The important part is that it's a finite description of the regular language, and this finite description should be effective in such a way that this description can be converted in one of the definitional mechanisms that we've seen before. So the description should be convertible into a regular expression, a non-deterministic automaton, or a deterministic finite automaton. As long as the program can do this conversion automatically, we are fine. But for simplicity, simply assume that if we say that the property of a regular language is decidable, we mean that the input of the program is a deterministic finite automaton, and then the program is asked to decide, does the property hold for the language described by this deterministic finite automaton? So for instance, the emptiness problem for regular languages is decidable. So we can create a program that takes as input a deterministic finite automaton for the language that we are interested in, and this program then tells us yes or no whether the language is empty or not. How does the program do that? Emptiness is very simple. For the emptiness of the language, it suffices to check whether in the automaton there's a path from a starting state to a final state. The language is non-empty if and only if there exists such a path. If there's a path from a starting state to a final state, then the automaton accepts at least one word, namely the concatenation of the labels along the transitions on this path. So the program can check whether there's such a path, and if there is, it answers the language is non-empty, and if there's no such path, the language is empty. Another decidable property of regular languages is membership. So given a regular language L and a word U, we can decide whether U is a member of L. How does this work? So first we transform the description of our regular language. It might be given as an NFA, a regular expression, and we first transform this into a deterministic finite automaton. So we have a deterministic finite automaton that accepts the language L. And now we can simply check whether this deterministic finite automaton accepts the word U. So what does the program do? It starts in the starting state and it follows the transitions according to the letters of U. If we end up in the final state, the word is accepted and otherwise rejected. So a program can easily do these steps. However, there's a practical problem hidden here, namely the problem of state space explosion. So we have a decision procedure, but it could be that it becomes practically difficult because we might need a lot of memory and a lot of time. Why does this state space explosion occur? If our regular language is given in the form of a non-deterministic finite automaton or a regular expression, then the first step, namely the conversion into a deterministic finite automaton, can yield an exponential increase in the number of states. Why is that? If you remember, for converting a non-deterministic finite automaton into a deterministic finite automaton, we've used the power set construction. So the states of the deterministic automaton are sets of states of the non-deterministic one. And if the non-deterministic automaton has n states, then in worst case, the deterministic automaton has 2 to the power n states. So that's an exponential increase in the number of states. And an exponential increase is never good. It already, if you have an automaton that's quite small with 100 states, then 2 to the 100 is quite big and possibly too big for a computer to handle. Now, what can we do to avoid this state space explosion? The trick is that we do not need to generate the entire deterministic automaton. We know what input word u we are interested in. So we will only generate those parts of the deterministic automaton that are visited when reading the word u. So we start with the starting state, and then we only generate those states of the deterministic automaton that we visit when reading the letters of u. And as a consequence, we avoid the exponential explosion. At most, we will generate as many states as the length of u. And this construction is called on-the-fly generation of the deterministic finite automaton. Inclusion among regular languages is decidable. So given regular languages L1 and L2, we can decide whether L1 is a subset of L2. How do we do this? Again, we assume that L1 and L2 are given as deterministic finite automata. Now we use the following property, namely, we know that L1 is a subset of L2 if and only if the difference of L1 minus L2 is empty. Right? This is the language containing all the words of L1 that are not in L2. So L2 is a superset of L1 if and only if this difference is empty. Now, how does this help us? It helps us insofar that we have seen how to construct a deterministic automaton for this difference. Given two deterministic automata for L1 and L2, we can construct a deterministic automaton for the difference, and then using this deterministic automaton, we already know that the emptiness problem is decidable. So we construct a deterministic automaton for the difference. That's the product construction that we've seen in one of the first lectures. And using this, we decide the emptiness problem of the difference. And by deciding the emptiness problem, we decide the inclusion problem. Another decidable property is equality of regular languages. So given regular languages L1 and L2, it is decidable whether L1 is equal to L2. How do we decide this? We know that L1 is equal to L2 if and only if L1 is a subset of L2 and L2 is a subset of L1. And we've seen on the last slide that this inclusion is decidable. So here we have two decidable problems, two inclusion problems. So we simply decide whether this is true and this is true, and then we can decide using this result whether the languages are equal.